one of the takeaway messages from last class should have been that what we read out as chemical shift for any given proton or carbon is dependent on the amount of other functional groups around that proton or carbon and the amount to which they shield or deshield that particular proton or carbon that we're observing. And that's where you get a difference in chemical shift. And it turns out that difference in chemical shift for simple functional groups is relatively consistent across molecules, particularly in the proton NMR. And so is something that you can look up a reasonable approximation of what your expected chemical shift would be from a table. And it turns out further that those changes in chemical shift that come by having different functional groups nearby a particular proton are roughly additive. And that kind of makes sense. If you've got a proton in an environment where functional group number 1 is deshielding to a certain amount, and you add functional group number 2, which is known to deshield that proton to a certain amount. Together, these deshield the proton by those two amounts put together, and so you've got a more or less additive relationship. We'll get to that more or less part in a minute. This is not strictly speaking additive, and we'll talk about why that is and how you might be able to sort of adjust for that in your mental calculation. So even though this is a very rough way to look at things, it turns out to be a pretty good, useful way of thinking about, well, where would my likely chemical shifts be for this particular molecule if I made the molecule that I'm looking for, or if I made this molecule that I'm considering as my candidate structure in my synthetic outcome, let's say. And so if you flip open your book to the page that mine naturally flips open to, because I look at this table quite a lot, you'll find this table. Okay.
Which page is it on?
Well, I don't know, because I don't know which version you have, but on mine it's 135. It's table 3.17 or 3.19, depending on which version of the book you're taking this out of. And it's also reproduced on the slide package that I just showed. Okay. So you find a list of functional groups next door to a methyl group, a methylene, and a methine set of protons. And so if you've got a fairly simple molecule that doesn't have very much nearby, except for example, a methyl group that's attached to an alkyne, you might expect that methyl group to appear in your proton NMR at about 1.8 parts per million, usually plus or minus 0.2, thereabouts. Okay. Similarly, if you have a methylene, a CH2, next door to an alcohol, you might expect that to appear at about 3.6 parts per million. But if you convert that OH to an ether, then you might expect that chemical shift to move upfield to about 3.4 parts per million. And this is really useful. It allows you to sort of get an immediate readout when you look at your crude NMR, for example, of did my etherification likely work, right? You expect these kinds of shifts. You'll note that the table is not full, okay? There are more entries for methyl groups than there are for methylenes, and there's more entries for methylenes than there are for methynes. And that's partly a fact of what kind of experimental data is available in the literature, and partly the fact that it's hard to get really isolated methynes sometimes because there's always other stuff going on. So here it's useful to remember something else that I told you last time, that every time you replace a proton with a carbon, the remaining protons move downfield to the tune of about 0.2 parts per million or thereabouts. Right? And so if you're interested to know the chemical shift of a CH that's attached to a sulfone, for example, there is no entry on that particular part of the table, but you might say, well, 2.9 is for a CH2, the corresponding CH is probably around 3.1. And that's actually a fairly robust way of calculating or estimating approximate chemical shift values. Okay. Now, this table is handy if you've got your book handy and you can flip it open. Like I said, mine falls open to that page. You can commit these values to memory if you want. And you probably will end up committing some of these values to memory. But there's a lot of them here, and it's sort of hard to remember all these. But it turns out that you actually know a lot of these values already, because each and every one of you who is an experimental synthetic chemist of some description, sooner or later sees some solvent in your NMR, right? So I think all of you probably have a pretty good idea of where ethyl acetate comes in the NMR. Probably all of you have a pretty good idea of where grease comes in the NMR or where THF comes in the NMR, because you see this stuff if you haven't, washed your dishes appropriately or left it on the vacuum pump long enough. Dimethylformamide you see in the NMR, okay? And so if you can remember where all of these solvent chemical shifts appear, that actually gives you a pretty good mental handle for where different functional groups appear. Because, for example, you know that dichloromethane, some residual dichloromethane solvent in your chloroform NMR comes in at 5.3 parts per million. That tells you immediately where a CH2 next to 2 chlorines appears. You can probably figure out then where a CH next to 2 chlorines would appear, or a CH3 next to 1 chlorine would appear, just based on sort of sensible chemical shift changes. And so knowing these chemical shift values or approximate chemical shift values for impurities in a few different common solvents can be useful. And because it's useful, people have gone and measured explicitly the proton and carbon NMR for a whole bunch of different impurities and solvents in several different common NMR solvents. And so the original publication of this kind of data is this reference here back in 1997 in JOC. And this is a real kind of go-to reference for pretty much every organic chemist. That's since been expanded and updated, and mostly what happened in the subsequent paper is that the organometallic community realized, hey, this is a really useful reference, but they haven't included a lot of the solvents that organometallic chemists sometimes use. And so they went back and they reran all of these and added another maybe 10 impurities. But the biggest thing was that they measured them in more different solvents, and they published that in this organometallics paper. And a measure...
10 authors.
There's more authors, yeah, but I don't know
I
that...
think it's because to get all the work done, they have more students.
Yeah, but I mean, there's people like John Burkaugh's on that other paper. John Burkaugh didn't go and measure any NMR, right?
His students might have.
Yeah,
Oh, yeah.
probably his students went and measured the NMR. But a measure of the importance of this actually comes if you read the opening paragraph on this 2010 update paper. It says, hanging above the desk of most every chemist whose work relies heavily on using NMR spectroscopy is NMR chemical shifts as common laboratory solvents as trace impurities by Gottlieb, Kotliar, and Noodleman, which is that initial paper. And that's exactly true. If you walk around my student office area, pretty much everybody has this earlier 97 paper posted up. And it's just so useful to know where all these impurities are, because you see them from time to time. And also, if you know what these impurities are, again, that allows you to estimate chemical shifts for your product. So, for example, if you look for acetone up here, you know where the methyl group of acetone comes in different solvents, 0.05 or 2.1 or whatever. That allows you to say, well, probably if I make a methyl ketone, it's going to be about here. And if I make a methylene next to a ketone, it's going to be about 0.2 ppm downfield. And a methine next to a ketone, another 0.2 ppm downfield. So remembering these impurity values allows you to move around. Okay, and we'll work through some examples of that to see how that works. I mentioned that chemical shifts are roughly additive, and so if you happen to have this table handy, this is another table that's in your book, table 3.20 in, I think, the most recent version of the text. You'll find this additivity table, which tells you that if you start with any particular CH, and we'll give your kind of default CH a chemical shift of about 1.5 parts per million, and you add any functional group, you should be able to add approximately this amount of chemical shift value and get to a sum that is approximately going to be the chemical shift for your observed proton. Okay, so for example, if you have nitromethane, okay, we would take 1.5 plus 3.0 and then minus 0.3 and minus 0.3 for the remaining two protons, and get to whatever that adds up to as our approximate value for nitromethane. Okay. I would say, personally, it's easier to just remember the number for nitromethane because that's a reasonably common solvent, and work from there. But